Are we live? It looks like we're live. If you've watched any of these, you know I'm new at this. Okay, we are. Fantastic. Just had to check, make sure everything was smooth on this end. Okay, we're going to jump straight into it. We are doing today the August 2022 Regents Exam, Chemistry. And yesterday I did a stream on the reference tables, going in detail on like everything that could possibly be asked about reference tables, how to use them, my tricks for using them. So hopefully we can get through the part A section pretty quickly. Part A is going to be the questions that are reference table and definition. You really should not touch a calculator for part A. So the goal for today is to get through that decently quickly using just the reference tables. So let me get in real close here so we can see. Obviously, you would bubble these in on the bubble sheet that you get. But that's all. Okay, very first thing, question number 1, it's always going to be an atomic theory question. Something about atomic structure. That is a guarantee. This one is asking, what is the number of protons in an atom that has a configuration of 2-5? Okay, a few ways to answer this. Number 1 is that protons are equal to electrons. That is true because we are talking about atoms. Atoms are electrically neutral, so protons are going to be equal to the number of electrons. And that means that we don't care about that. That means that obviously 2 plus the 5 is going to give us 7, right? Electron configuration. This is telling us that we have a nucleus. And in the first shell of electrons, we have 2. And then in the second shell of electrons, we have 5. So that nucleus is going to be in the second period of the periodic table. Configuration 2-5. We can look it up just to say that we did. We head to the periodic table. This one comes in sideways, so I have to rotate clockwise. 2-5 is going to be nitrogen right here. And this is the electron configuration. We have a key right here that tells us that that's the electron configuration. 2-5 is going to have 7 protons because it's got atomic number 7. The atomic number 7 tells you, hey, this is nitrogen, and hey, nitrogen has 7 protons. If it didn't have 7 protons, it wouldn't be nitrogen. And if it has 7 protons, it has to be nitrogen. So that is that very first question. It's got 7 protons. Okay, question 2 is a vocabulary question, which I kind of love, but I also kind of hate because I have always described chemistry kind of like a language. Teaching chemistry, I give students like, I don't know, 200, 400 vocabulary terms. I don't know what it is. It's one of those things where if you don't know the vocab terms, you are going to absolutely flop in part A, which is a terrible place to flop because those are kind of like the easiest questions. This is specifically asking about the wave mechanical model, which you may have also learned as the electron cloud model. Those two terms are the same thing. It just means the modern model of the atom, where the electrons go into clouds instead of orbits. So just from vocab, the region of the most probable neutron location. Neutrons are always in the nucleus, so that's no. Most probable electron location is correct. The straight line path of a neutron, they are not moving. And then this one, straight line path of an electron. Electrons, they move, but they're orbiting a nucleus. They are not moving in straight lines. This is trying to trip you up and confuse you with collision theory. Collision theory is, or rather, kinetic molecular theory. Kinetic molecular theory just describes how gas particles specifically move, but that's like entire gas atoms or entire gas molecules, not the subatomic particles. Okay, next up, number 3, in the ground state. There you go, vocab term. You have to know what ground state means, otherwise you can't properly answer this question. Which shell of a potassium atom has an electron with the greatest amount of energy? All right. This is truly asking you if you know what a valence electron is, because the electron with the greatest amount of energy is a valence electron. The electron's energy is related to its proximity to the nucleus. The closer it is to the nucleus, the less energy it has. The further away it is from the nucleus, the more energy it has. I like to describe that kind of like the freedom an electron has, right? Protons and electrons are positive and negative. They're attracted to each other. If they are super close, they're super attracted. That proton is kind of controlling where the electron can go because they're electrostatically attracted. But as that electron gets further and further and further and further and further away from the nucleus is shielded by all the internal electrons. Plus, they're further away. So the electron that's further away has more freedom and can move about better. So the one with the most energy in a potassium is going to be the 4th energy level. And we're just going to cross-reference this with the periodic table real quick to make sure that we're doing it right. Because they ask this question in a variety of different ways. I could see them doing something like 2nd, 3rd, 4th, and 5th to kind of mess you up, and you just pick the biggest number. So looking at the reference table, potassium is K, not P. If you have to look it up, you can cross-reference on table S also. Potassium's right here, symbol K. It has 2881 because there's 4 digits there. It has 4 energy levels. It's also in the 4th period of the periodic table, which tells you that it has 4 shells of electrons, and they run in order from left to right. So your nucleus would be right there, and then the first level has 2, then 8, then 8, and then finally the valence has just 1 electron in it. So obviously the 4th level is the answer. Okay. Feel free, of course, to ask questions in the chat box. If you got questions, it's what I'm here for. That's why I'm doing it live instead of recorded. Okay, question 4. Which phrase describes 2 atoms that contain the same number of protons but a different number of neutrons? Again, this is a vocab question. They're giving you a definition and asking you to know the term. The definition of 2 atoms that have the same number of protons but a different number of neutrons would be an isotope, and they would be isotopes of the same element. I'm going to give you some examples just for the sake of learning here. This would be like carbon 14 and carbon 12. They each are carbon, so they're each going to have 6 protons. This mass number here tells you the number of protons and neutrons together. So for carbon, that 14 minus the 6 protons that it has means that this has 8 neutrons alongside its 6 protons. This is carbon, so it must have 6 protons. It has 12 things in the nucleus, meaning the leftover 6 must be the neutrons. Those are isotopes. Ions are going to be things that have charges. So that would be something like chlorine, which has lost an electron and takes on a -1 charge. At that point, we call it chloride. We could also have something like sodium, which loses an electron and is going to become a positive ion. A mixture of different elements is just a mixture. And nuclides of different elements, I don't love that term. Don't love it. Mostly because of table and the radioactivity table. Truthfully, I would have written to the Regents Board about this question. I don't like option 4, but it obviously is option 2. Okay, question 5 is kind of a rephrasing of question 4. This is an August test. People have opinions about which tests are the easiest ones. Some of them are just ridiculous. Whoever wrote this test put too many isotope questions on here. Okay, question 5. All atoms of an element have the same number of protons. That is your correct answer. Like we were saying earlier, if you have 6 protons, you have to be carbon. I think it was question 1. If you have 7 protons, you have to be nitrogen. If it's an atom of the same element, it has to come down to the number of protons. That's how we decide whether it's carbon, nitrogen, gold, copper, lithium, uranium. It's all based on the number of protons. That's really what the protons are good for. The mass number is the sum of protons and neutrons, and choice 3, the number of neutrons. Those two things, those two answer choices, both include the number of neutrons. And number of neutrons is wrong, so mass number by default would have to be wrong. The number of protons, on the other hand, is the correct answer. Now, the atomic mass is a weird answer choice as well, because if you look at carbon on the periodic table, it has a mass of 12.011, and that mass is like a hypothetical mass, right? It's the average of all of the carbons in the whole universe. If you were to pluck just one of them, you would get it's carbon 12, or maybe carbon 13, or maybe carbon 14. They absolutely have to have the same number of protons. The atomic mass is kind of a weird answer choice there. Mostly because the mass on the periodic table represents the average carbon out there in the world. Okay, for question 6, which group 15 element is classified as a metal? We are going to check out the periodic table. Nitrogen, arsenic, phosphorus, and bismuth. Oops. Okay, so we are looking at... Why is this not working now? We're going to erase this so that we have a clear spot. We are looking at nitrogen, phosphorus, arsenic, and bismuth. And this is a great place to also just chime in about periodic table trends. Right here, nitrogen is a nonmetal. Nonmetal, so is phosphorus. Nonmetals are towards the right side of the periodic table, and because this is technically to the right of that staircase line, right here where boron and aluminum and silicon are, nitrogen and phosphorus are to the right of that and not touching it, meaning that they are nonmetals. Arsenic, on the other hand, is kind of nestled in the L of that staircase. They're either in the L or in the 7. Because arsenic is touching two sides of the staircase line, that is going to classify it as a metalloid. And then bismuth down at the bottom is to the left of that staircase line, so it is going to be classified as a metal. This also goes along with the trend of metallic character. Going down a group, your elements are becoming more and more metallic, i.e. they're more willing to lose electrons. So bismuth is going to be the metal in that situation out of those that are listed. Let's go back. Bismuth, Bi. Sometimes they'll give us to you as symbols, and other times they'll give you the names. So if they give you the names, if you're nervous about it, look it up on table S. You have that option. Okay, moving right along. Question 7. Compared to the number of electron shells and radius of an aluminum atom in the ground state, a boron atom in the ground state has blank. Okay. This one would be great to do side by side with the reference table here. So let's do that. We're comparing aluminum and boron. Sorry, this is not my computer. I'm borrowing my husband's computer, so I'm not super savvy here. I appreciate your patience. Slide this over. Okay, now we're looking at question 7. And over here specifically, we are looking at boron and aluminum. And again, here, they're giving you the names. If you forgot that boron is just B, then look it up on table S. Do not, if you're not feeling confident about it, do not trust what your brain is telling you, because your brain is going to be exhausted. They're giving you the reference tables, use them. Okay, we're talking aluminum and boron, which is AL and B right there. Okay, so This is one of those annoying Regents things where we are looking at whether we have more or less electron shells and then how the radius compares. Boron is going to have fewer electron shells. And there's two ways to figure this out. Number one is looking at the electron configuration. For boron, we have 2 digits. We have a 2 and a 3. So that's the first level and then the second level. And then in aluminum, we have 3 digits. So aluminum has 3 layers of electrons. It has more electron shells. So this question is saying boron in the ground state has, and it's going to be fewer electron shells. So those two are out. And then the next question is about radius. And this, I really don't think is that much of a chemistry question per se. This, at this point, becomes a logic question. And that is because if you have boron here with 2 energy levels, and then you have aluminum here with 3, 1, 2, and then 3, obviously the aluminum is going to be bigger because it has an extra shell of electrons. Also, when it comes to radius, we're talking about regular atoms in the ground state. That is what is represented on table S. So you could look it up and go get some numbers to help you with that one. And I'm sure you could reverse engineer it. The smaller one would have to have fewer electron shells. So boron is smaller, and it's got fewer electron shells. Okay, of course, feel free to ask any questions you have. Okay. Moving right along. Question 8. Hydrogen sulfide, H2S, is classified as a blank. Okay. Again, this is a vocabulary question. Don't we love this first section? It's all just vocab. If you are stressed and studying last minute, I have 2 recommendations. Number 1, spend 2 hours or an hour and a half, watch it like 1.5 speed, whatever, my reference table stream from yesterday. Then go open up your chemistry textbook and read the glossary. If you are doing a last minute cram session, that's what you need to do. All right. So right here, this is asking us, what are we looking at? Is it a compound or is it a mixture? And then a second piece, which we know. We love these questions, right? They're so good. Hydrogen sulfide is a compound. The reason I know it's a compound is because these, the H and the S are smushed together. There's no space between those elements. So it is not a mixture. Mixtures are going to have, like, it would be hydrogen and sulfur. Or it would be hydrogen 2 plus sulfur. Or it would be something like H2S aqueous. That could be a mixture because it would be mixed with water. Just it on its own is going to be a compound. Compounds, by definition, come in fixed proportion. What this means is that every time I have 2 H's, I'm going to have 1 S. Every time I have 1 S, I'm going to have 2 H's. The variable proportion means that the amount of stuff can change. So if you think of salt water, sometimes you can have very salty water or water with just a little sprinkle of salt in it. And it's still salt water, it's just the amounts are variable. They change. So compounds do not do that. In water, for every 2 H's, there's 1 O. In every sodium chloride, there's a 1-to-1 ratio. That's what the fixed proportion is. That is what makes it a compound. For that reason, they're also pure substances. Okay. Number 9. Structural formulas differ from molecular formulas in that a structural formula shows the blank. Okay. So here we go. A structural formula example would be this. H bonded to O bonded to H. Draw your water Lewis structures like this because you'll remember that it's polar. Because it's asymmetrical. Because it's lopsided. So a molecular formula for water would just be H2O. So that's the difference. The structural formula is going to show the arrangement. It shows how they are bonded together. The number of atoms is the same in each of them. We have 3 in total, 2 hydrogens and 1 oxygen. The ratio of atoms, even though it doesn't explicitly tell you that it's 2 H's and 1 O, it takes one brain cell to just count them. And then the types of atoms, obviously, hydrogens and oxygens. It's just the arrangement. It shows you how it's built. Okay, moving on. Which type of reaction occurs when a compound is separated into its elements? Okay. Based on these answer choices, there's one answer, but there could be a second answer. Okay. Let's do this. We have water, and it's going to break into its elements, H2 and O2. Okay, that's not balanced. Let's balance that. We would have to put a 2 right here to get me the 2 oxygens, and I'd have to put a 2 right there to get 4 hydrogens. Okay, there's my balanced equation. This is a decomposition. Same as living environment, decomposition, you break it down. This could also be done by electrolysis, which is just like a lab process, really, but it's also a reaction, kind of, sort of. The electrolysis really just means that you're using electricity to make the reaction happen. It's the provider of the activation energy, let's say. So really what would happen is that you take the water, you run an electrical charge through it. When it's like just the right charge, it's able to break the hydrogen-oxygen bonds. The hydrogen and the oxygens, they split up. You may have done this in a Dalton's Law lab, possibly, and collected the hydrogen and the oxygen. You listened to the pop, and the lit splint flared up. So you may have actually done an electrolysis. An electrolysis can be a decomposition, but in this case, it's a decomposition. A synthesis is when you're going to make something. So it would be like sodium and chlorine come together to make sodium chloride. The single replacement is where you have somebody stealing a spot. So we would have, let's say, magnesium chloride and potassium. And then the potassium is able to kick out the magnesium and says, hey, that chlorine belongs to me now. So it would be 2 KCl and a magnesium. And I would need a 2 right there. Sorry, this Cami stinks. Anybody else hate Cami? So that's the single replacement, and then the double replacement would be A, B, C, and D, and they swap. The thing here on the swap is that when we write chemical formulas, we always write them positive, negative. The positive will not bond with the other positive, and this positive has already been paired with this negative B, so A will always pair up with the D, whatever it is, and then C would be left to pair with B, but we would write it CB because, again, we always write the positive thing first. So that would be the double replacement. There's a bunch of those. Mostly solubility, but also your neutralization reaction, where acid and base make salt and water. That's also a type of double replacement. But that's like the 4 basic inorganic reactions. All right, let's keep moving. That's page 1. Nope, it's not page 1. We have one more on page 1. Okay, which 2 terms represent categories of compounds? Okay, this is a weird question. I don't know who even wrote this question. It's just vocab. Chemical and physical, there is no such thing as a physical compound. It's just a silly thing. Chemical compounds and molecular compounds, I don't know what that is supposed to mean. Chemical compounds are just chemicals. Ionic and physical doesn't make any sense. And it is ionic and molecular. That's really what it is. Ionic means it has ionic bonds. So electrons are transferred from the positive to the negative, but typically from a metal to a non-metal. And a molecular compound is just something that has covalent bonds. I don't know why they decided to just name them molecular. They did. That's what they decided. Molecular things are things that have covalent bonds. Lots of examples of that. You have H2O, CO2, H2S, NH3, all of those are molecular compounds. Ionic things would be like potassium sulfide, sodium chloride, blah, blah, blah. The list goes on and on. Okay. I am monitoring the chat box if you have questions. I just don't want to sit here waiting for questions. I am willing to go back if you have a question, though. Not like a million years back. Okay. Question 12. This is one I would recommend writing out. When an atom of hydrogen and an atom of chlorine combine to form a molecule of hydrogen chloride, a bond is blank. Okay. An atom of hydrogen. This is super specific. It means just a single H. Typically, H is going to come in twos because it's a diatomic. But this is specifically talking about a single atom of hydrogen, and that is going to be pertinent to answering the question. So make sure to read this carefully. We have an atom of hydrogen, and we want it to react with an atom of chlorine. Same thing applies here. Chlorine is also a diatomic. They are going to combine to form a molecule of hydrogen chloride. This is an example of a synthesis, by the way. Two things kind of like squishing together. Okay. I hope your teacher taught you this acronym, because this is a really good acronym. This is BARF. We went over this in the last test also. So in BARF, and excuse me, this keyboard is going to be very loud. BARF is just an acronym to tell you what happens when bonds are broken or bonds are formed. When bonds are broken, energy has to be absorbed. The reason is because atoms are more stable when they're bonded. And then when you break them apart, you have to put in energy to break apart that bond. They're happy being bonded. So at that point, you have to put in energy to break them apart. When they form a bond, I like to think of it like a sigh of relief. They're like, my life is so chaotic. I don't have my octet. And then finally they bond and they go, oh, I got my octet. Awesome. So they release a bunch of energy. So in this case, the hydrogen and the chlorine are doing exactly that. They are bonding together. They're getting that octet and they are so happy about it. So for that reason, not only are we forming bonds, but the energy is going to be released. So we are forming bonds and energy is released. Okay. Number 13, very similar to that question 5 maybe. All atoms of the element vanadium must have the same atomic number. Whoever wrote this test really loves isotopes and really loves basic atomic structure. Mass number of vanadiums can change. Those would be isotopes of vanadium, so that is not a quality answer. The number of neutrons plus electrons, we don't ever really do anything with that sum. I've never seen it ever in action. And then finally, the number of protons plus neutrons is the mass number. So they use the same answer twice, which is an indication that it's a wrong answer. Either that, or they're going to have to throw out the question because they've added the correct answer choice twice. These things get checked over and over and over and over and over again. Don't assume that that's the case. So just on that alone, you rule out 2 and 4 because they're the same answer. And again, all atoms of vanadium must have the same atomic number. I believe it's 23. Come on. Yes, vanadium right here. If it is vanadium, its atomic number is 23. If its atomic number is 24, it's not vanadium, it's chromium. If it's 22, it's titanium. That's just the way it is. I'll be honest, this test is kind of boring. In terms of teaching, I feel like it's the same thing all the time. Which sample of matter can be separated into two different substances by physical means? They're doing it again. That is, they give you the definition and they're asking you to find the term, but in this case, they're not asking straight up for the term. They're asking you to apply the term. So a sample of matter that can be separated into two different substances by physical means must be a mixture. Okay? On top of that, we then need to go figure out which of those answer choices is the mixture. Liquid bromine is an element. If you find it on the periodic table, it's an element. It's called the periodic table, spoiler, of the elements. If it's on the periodic table, it's not a mixture. It can be part of a mixture, but it itself is not a mixture. So bromine, not it. Gaseous propane. Propane, you should know, is C3H, double it plus 2 is 8. It is a chemical, it's a compound. It is a compound. Because for every 3 C's, I will have 8 H's, and that's what makes it propane. If it were anything else, it wouldn't be propane. So this is an element. This is a compound, so that's not the answer. Solid sodium acetate. This is just an ionic compound. It's a sodium bonded to an acetate. I always forget if acetate is +2 or -2 or -1. So let's go look it up. Your 8s and ites are going to be found on table E. That's where we find all of the polys. I think it's a 2. C2H3O2 -2? No, it's -1. Good thing I looked it up. It's right there. So because it's a -1, C2H3O2, no need to crisscross because the sodium's +1. Even though it's a giant compound, it's still just a compound. The aqueous magnesium sulfate. The key here is the aqueous. Aqueous just means mixed with water. And it would be some amount of MgSO4. Each of those has a 2 for the charge. Magnesium is +2. Sulfate is -2. When they crisscross, they drop out. So it is the aqueous magnesium sulfate. It is water as well. And they're just mixed together. And by physical means is telling you that you could evaporate out the water and be left with the magnesium sulfate. Another separation of mixtures question for number 15. 2 liquids can be separated by distillation due to a difference in, and this is just vocabulary and knowing your stuff. Distillation is a difference in boiling point. I am going to see if I can pull up a picture of a distillation and just run through it, because I know that this is really hard for a lot of kids. Encyclopedia Britannica. Okay, I'm going to explain to you how this works. Okay, here's what we got. In this case, we would have a set of homogeneous, this is a terrible example that they have here. Let's say it's alcohol and water. Typically, we're going to do this with homogeneous liquids. 2 liquids that mix together beautifully. We're going to heat them up. The reason is because they have different boiling points. They are going to warm up and warm up and warm up until the first thing starts to boil. Let's say it's alcohol and water. The alcohol will start boiling at 79 Celsius. And when that happens, you will have the alcohol vapor rising up. As it's rising, you know that the thermometer is going to tell you it's 79 Celsius because it's alcohol and it's boiling. Water will not be boiling because the water won't boil until the temperature is 100 Celsius. But you also know that temperature doesn't change during a phase change. So the temperature is going to remain at 79 until all of the alcohol has evaporated. It's boiled and evaporated. it is forced into this tiny little tube, which sends it over here. And this is like a tube in a tube. And the inner tube is where the alcohol vapor is. And the outer tube has cold water circulating through it. And the idea is that the alcohol vapor will pass through and it'll touch the glass, and the glass will be cold because it's containing cold water, right? And then the cold water will make the alcohol vapor condense. It gets cold enough that it condenses back to a liquid. That's why this is called a condensing tube. And then eventually it will drip out into the receiving flask, which is going to pick up whatever it is. You don't typically do this with salt and water because the salt is going to get stuck in this boiling flask. Typically you would do that in an evaporating dish, which is really like a little porcelain bowl, typically a little thicker, and you would have the salt in a place where you could scoop it out quite easily. You don't typically use a distillation to do something that's aqueous. It would mostly be for homogeneous liquids. So that is how a distillation works. Then we have concentration. You could maybe do that with a semi-permeable membrane. Possibly. You're not going to be able to do that easily. My guess would be you would have to like do a chemical reaction and precipitate something out simply because you're not able to easily separate something by concentration. Conductivity, not a way to separate components. It's a way to distinguish components. You could have a mystery material and then try to run a charge through it and find out if it's conductive to figure out if it's a metal or if it's a pure metal. Metals also have different conductivities, which you will learn if you take physics. And then the heat of fusion is just the amount of energy it takes for a sample to freeze or to melt, which doesn't necessarily separate two liquids. You could freeze or melt to try to separate liquids, but the literal constant won't help you with that. So that was a strange question. I'm just surprised that the other three answer choices weren't actually ways to separate mixtures, but that is that. Which unit can be used to describe the to express the concentration of a PbCl2 aqueous solution? Okay, that is lead 2 chloride. To express the concentration. Okay, I would tell you to go check out table D. Which do I want? This is what I want. If you didn't know, you would look it up and you would find one for concentration. And we're looking in the quantity section here. And parts per million and molarity each are going to describe concentration. So I would just use that. So the answer is parts per million. Pascals measures pressure. Kelvins is temperature. And kilojoules per gram. Kilojoules per gram. Joules per gram. Heat of fusion, heat of vaporization. It's not concentration. Like I said, it's right here in question 15. It is related to the amount of energy needed to conduct a phase change. Not going to help you with the concentration. The concentration is how much stuff is in your other stuff. How much lead 2 chloride is in the water. You don't want lead chloride, at least in your drinking water, you don't want it there. Not very good for you. So you would want to know how many parts per million were in there to decide if it were safe or if it were unsafe. 17 is another one of those classic Regents questions where the answer choices are so annoying. Moving on. Compared to the freezing point and boiling point of water at 1 atmosphere, a 0.5 molar aqueous solution of NaCl at 1 atmosphere has blank. Alrighty. We are at 1 atmosphere for both of these. We are comparing water to a 0.5 molar aqueous solution of NaCl. This is colligative properties. There's a whole video on my channel on colligative properties. Colligative properties, more or less, is how much, it's a change in the physical properties when you dissolve stuff in water. So if you dissolve salt in water, even sugar in water, you are going to raise the boiling point. It's harder to boil. You're going to drop the freezing point. It's harder to freeze. You have to remove more energy in order to get it to freeze. The vapor pressure is going to, it's going to be harder to evaporate. So your vapor pressure is going to decrease. It's going to affect surface tension, and it's also going to affect osmotic pressure, which is not super important in Regents Chem. Okay, so the way that I describe this, when you add salt to water, you are going to expand the liquid phase. What the heck are you talking about, Kelsey? Let's imagine a thermometer. This is a thermometer. Trust me, it's a thermometer. This is 0 degrees Celsius. This is 100 degrees Celsius. That is the melting / freezing point of regular water and the boiling point of regular water. But once you add salt to it, you now can boil somewhere around, I don't know, 105, let's say, 106, 104. It depends on how much stuff you're adding. It depends on the concentration. It also depends on the number of particles that come out. You're also going to drop the freezing point. So let's say we get down to -5 degrees Celsius. You can see here that from 105 to -5 is all in the liquid phase now. So you just expand the liquid phase up and down, and that's the way to remember it. Add salt to water, you expand the liquid phase. Boiling point goes up, freezing point goes down. Now back to that number of particles that comes out. NaCl is going to break apart into sodium and chloride. If I had, let's say, K2S, K2S would break into K, K, and S-2. If I had equal number of moles of sodium chloride and potassium sulfide dissolving in water, this would have the greater effect. It would expand the liquid phase more dramatically because we have 3 particles interfering with the water's original physical properties, whereas here I only have the sodium and the chloride. I only have 2 particles interfering with those properties. Okay, so we're just comparing regular water to the sodium chloride. So if we are expanding the liquid phase, we are going to lower the freezing point, but have a higher boiling point. It's going to be harder to freeze. You have to remove more heat, and it's going to be harder to boil. You have to add more heat. And that is answer choice 2. And again, whole video on that on this channel if you need some help there. Or, of course, feel free to ask questions now in the chat box. Okay, moving on to question 18. Which form of energy is converted to thermal when propane burns? Okay. Mechanical energy is like, first off, not used in chemistry. That's a physics term. It is your potential plus your kinetic together. It's often related to machines. That's why it's called mechanical. Nuclear would have to involve some type of nuclear reaction. Electrical, obviously, would have to involve some type of battery. It's chemical. In chemistry, chemical energy and potential energy are the same thing. In this case, the propane would be C3H8. We're burning it in the presence of oxygen. The product of every combustion reaction is carbon dioxide and water. So obviously we're breaking bonds. We're forming some new ones, but we're mostly breaking bonds here. When we break bonds, we have to absorb energy, and when we release energy when we're forming bonds, but the energy that is stored in that bond is called chemical energy. Moving to 19, this is a great vocabulary term. Again, a whole video on this channel on this. Kinetic molecular theory. Which statement best describes why an ideal gas can be compressed to a smaller volume? The kinetic molecular theory has 6 rules that describe how ideal gases work. Ideal gases don't actually exist. We talk about ideal gases because the math is a lot easier when we allow for ideal gases. And it's not far off enough from what it actually is for it to matter. So don't Google it because you'll cry. But there's the van der Waals equation, or the van der Waals equation. And that's really how real gases interact with each other. For realsies, all particles are going to have intermolecular forces to whatever is around them. We pretend for ideal gases that they don't have intermolecular forces, just because it makes the math easier, and the difference between those two mathematical answers is not significant enough for us to care and do the calculus. So the motion of gas particles is circular and orderly. No, it's not. Gas particles kind of act like a big box of bouncy balls that you throw down the stairs. They bounce, they hit the wall, they bounce off, and they bounce it off of somebody's head, and then they bounce and they hit the wall, and they bounce off the railing and bounce off the stairs, and they're moving in straight lines. They're not like cartoon wind blowing around in circles. The force of attraction between gas particles is strong. No. These gas particles are super, super far apart from each other, so most of the time they're not really feeling intermolecular forces. We know for realsies that they'll like fly past each other, and they will feel IMFs. But the kinetic molecular theory says, no, they don't. We're going to do algebra instead of calculus. They don't have intermolecular force. So there's no force of attraction between them. There's no force of repulsion either. Remember, IMFs are both attracting molecules together, but they are also repelling. When gas particles collide, the total system energy decreases. No, gas particles have elastic collisions, which really means that when they smack into each other, they will split the energy between the two, but there's no loss to the atmosphere. There's no loss to the environment. So let's just say, for the sake of argument, a particle with 100 units of energy hits a particle with 50 units of energy. They'll collide, smack, and go in their opposite directions, and they'll go off with 75 each. But the total is going to remain 150. So they're not losing any energy to the surroundings. And then number 4, which is going to help us to explain why gases can be compressed, is because they're really far apart from each other. What you do is you take that gas, and the particles are really far apart. They take up their entire container. And there's a lot of empty space between them, and you squeeze them and push out that empty space. And if you push them enough, you can push them into a liquid. For question 20, under which conditions of temperature and pressure does a sample of propane behave least like an ideal gas? Okay, this is interesting because they almost never ask it as a least. For moving forward, ideal gases are going to follow this silly acronym that is PLIGHT. They like a low pressure, they are ideal gases, and they like a high temperature. When they have a low pressure and a high temperature, the particles are far apart from each other, and they're moving around very quickly, and they're not able to feel IMFs. And this is going to put them in that box following those 6 rules of the kinetic molecular theory as best as possible. Under those conditions, real gases will be as close as possible to ideal gases. This question is asking for the opposite. Which one is going to behave the least like an ideal gas? So in this case, we don't want a low pressure, we want a high pressure. We want our particles squeezed close together. So that's going to be the atmospheres, right? Atmospheres is measuring pressure. And if we have a low temperature, the particles are going to move slow. They're going to be closer together. And that's going to be the Kelvin measurement. So we want a low temperature. So we're not going to take these options that are giving us 500 Kelvin, because that's a very high temperature. Remember, room temperature is about 300 Kelvin. So we want this 250, that'll work, but instead of having a low pressure, we want a high pressure. So that is going to be choice 2. '21. Ooh, I love these questions. Okay. Compared to a 1 liter sample of carbon dioxide gas in a sealed, rigid container at STP, a 1 liter sample of methane gas in a sealed, rigid container at STP has the same blank. This, you may not know, is Avogadro's law. Avogadro's the really annoying guy who came up with a mole and made us all do stoichiometry. He didn't actually come up with the mole, though. He came up with this concept that if you had the same number of, if you had 2 gases under the same conditions of temperature and pressure, STP and STP, they have the same temperature, they have the same pressure. We have the same volume. He says it doesn't matter what the gas is. It could be hydrogen, which only has a mass of 2. It could be carbon dioxide with a mass of, 40? He said it doesn't matter. They will have the same number of particles. And that's mostly related to the fact that gases have a bunch of empty space between them. That's how he's able to do it. So this is the number of molecules. They will have the same number of molecules. If that volume happens to be 22.4 liters, then you get a mole of gas. And he just came up with that concept. And then a bunch of physicists finished the job and gave us stoichiometry like a bunch of knuckleheads. But it's true. They will have the same number of molecules. They're under the exact same conditions, so they'll have the same number of molecules. Chemical properties will not happen. They're going to have different boiling points, different melting points. They're going to have different reactivity. Well, that's physical properties. The reactivity is chemical properties. They're both nonpolar, which would work. Their molar mass, this is 12, 13, 14, 15, 16, and this is like 40. That's a silly one. And density, not happening. Definitely not happening. Carbon dioxide is decently heavy for its size, so the density of carbon dioxide is definitely more than methane. And again, that's Avogadro's law. You only have to know Avogadro's law in concept. You don't have to know how to do the math for it. 22, a chemical reaction occurs when blank. Okay, in order for it to be a chemical reaction, we have to have some type of bond breaking and bond forming. So if I have H2O gas becoming H2O liquid, that's a phase change. And phase changes are not chemical changes. They are physical changes. Same thing here from liquid to solid. Oxygen liquid becoming oxygen solid. That takes a lot of lab work to do, but it's here. You could have it. That would not be a chemical reaction. Again, that's a phase change. And then finally, this last one will count. Oxygen becoming ozone. O2 has a double bond, and it looks like this. And if you want to add a third oxygen in here, then you would have to break one of those bonds. You have to draw another oxygen, and it's a deal, okay? That is going to make it a chemical reaction. 23, what is the purpose of adding a catalyst to a chemical reaction? This is more or less related to the definition of a catalyst. Notice how we've done no math. It's part A. There's no math in part A, which we all love. Okay, so definition of a catalyst. Catalysts are going to make it easier for reactions to happen because they give the reaction a shortcut. And in doing that, they are going to decrease the amount of energy needed. Which is why answer choice 1 is kind of sketchy. Okay, if we look at one of those potential energy diagrams, let's just do a quick sketch. Let's say we have an exothermic reaction. Exothermic, because we're losing energy over time. Energy is exiting. These are my reactants. These are my products. And we're measuring potential energy here. And the distance from here to here is delta H. That's the heat of the reaction. If we decrease the potential energy of the products, that would mean that we're dropping this plateau right here, which we are not doing with a catalyst. The catalyst is going to go like this. And it's going to affect the activation energy, which is this right here. The amount of energy needed to get the reactants to convert into products. So we're not increasing potential energy either. Converting solids to liquid reactants. A catalyst may help with that, but that's not the purpose of a catalyst, like, overall. It is going to provide an alternate reaction pathway. Really what that means is that it gives a reaction a shortcut so that we can reduce the activation energy, which is the energy needed to start a reaction. The way I like to explain this, like, for real, is lighting a match. Lighting a match is the kickstart of a combustion reaction. You can light matches by, like, scraping them on the sidewalk. You can scrape them on a rock. I used to scrape them on the chalkboard of my classroom. Depending on the texture of the surface, you can scrape a match on a lot of things to get it to light. But if you have a match box with a little striker on it, you only have to travel a very short distance to get the match to light. And the striker is going to count as the catalyst. It's a quick way to get the reaction to happen, and it's going to require less energy. 24, this is the definition of entropy. Systems in nature tend to undergo changes that are going to lower their energy, but increase their disorder. Nature is messy and lazy. Nature does not make us like beautiful manicured gardens. Nature is going to give us the woods where all of the plants get tangled up in each other, and that's a lot of disorder. There's no like crisp clear paths. Your shrubs are not perfectly tended to and shaped. And the reason for that is because we are looking for a low energy situation. So that low energy, great disorder, that's what entropy is. That's what nature is going to do. That's just a definition question. 25, which reaction occurs at the anode of an electrochemical cell? Okay, this is a good one. The anode is the, well, you gotta know the definition here, but the anode is the electrode where oxidation takes place. And you may have learned an ox and the red cat. Anode is where oxidation occurs. The reduction occurs at the cathode. And that is that. That's going to be true no matter what type of electrochemical cell you're working with. Neutralization is just acid-base neutralization. You don't need an electrode for that necessarily. Substitution is an organic reaction. I mean, even sometimes that type of stuff, you know, anode is a redox term, right? So you wouldn't use the acid-base term and you wouldn't use the organic term. So that would put it between oxidation and reduction, which at least gives you a 50-50. But it is the anox and the red cat can help you with that. Okay, question 26. As more NaCl is dissolved in a dilute, unsaturated sodium chloride solution, the conductivity of the solution blank. Okay. We are dissolving more and more and more of the sodium chloride in the solution. So the concentration is not decreasing. So we don't want that, and we don't want this, because the concentration is literally rising. That's very silly. So the question is, does the conductivity go up or does it go down? And the conductivity will increase. The more ions you have dissolved in the solution, the better the solution will be able to conduct electricity. And this term is related to electrolytes. An electrolyte is just a solution that can conduct electricity due to the presence of mobile ions. Now, not in part A, but you could get something like this in part B. It is possible. Sodium chloride is soluble in water, and you know this because you're a human being. It dissolves in water. They could also give you an option of like silver chloride. Silver chloride does not dissolve in water. It just sits on the bottom of the container. And if it's sitting on the bottom of the container, there are no mobile ions. So that won't conduct on its own. So just be mindful of that looking into this electrolyte thing. You have to have those mobile ions. You can't just have stuff dissolved or mixed with water. 27. Which substance always forms an areneous acid? Which substance always forms when an areneous acid reacts with an areneous base? Okay, this is the definition of a neutralization reaction. Again, I'm real quick on a regular computer. This is my husband's computer, and this keyboard makes me crazy. The neutralization reaction, you'll always have an acid reacting with a base, and you are going to get some ionic salts and water every single time. So that's it. It's just simply the definition. Water is the product. If we look at an example here, let's just keep it super simple. Let's say we have hydrobromic acid reacting with, I don't know, lithium hydroxide. In this case, let's do the double replacement, right? This would give us, we have a positive, negative, positive, negative. H is going to bond to that OH, which is HOH or H2O. And then you'll have the lithium and the bromine making lithium bromide. And that's it. This would be the ionic salt, and then you have water. That is not salt. That's salt. The ionic salt and water. Holy smoly, shush. Okay, question 28. This is a beautiful reference table question. We love reference table questions. You know why? Because you just need to know where to find the answer. Which symbol represents a nuclear emission with the greatest mass and the greatest ionizing power? Okay, let's look at the reference table. I'm going to throw this phone out the window. I'll find the table and then I'll make it look nice. Here we go. What is this? Table O? Table O. Nuclear chemistry symbols. We have alpha. We have beta plus. beta minus, and gamma. Which of these has the greatest mass? Well, that's the alpha. Alpha has the 4 on top, which is the mass number, and alpha particle is the same as a helium nucleus. It has 4 particles in the nucleus, 2 protons and 2 electrons. No, 2 protons and 2 neutrons. So that is going to have the greatest mass and therefore the greatest ionizing power. Gamma has no mass at all. Gamma is just energy. Ooh. Okay, 29. One potential benefit of nuclear fusion reactions is... Okay, so benefit, obviously it has to be a good thing. I don't know how a reactor meltdown or an uncontrolled chain reaction would be a good thing. So let's just take those out right away. Who wrote these questions? Nuclear fusion. We are going to get a lot of energy. That's why we like the idea of nuclear power. Because you can have a tiny amount of nuclear material and turn it into a heck of a lot of energy. Meanwhile, if you were doing some type of like fossil fuel or hydropower or even like burning wood, you would have to have a lot of matter to create a lot of energy, where in the case of nuclear, you can do a small amount of matter and a large amount of energy. And that's really the benefit. Radioactive waste materials, I'm going to go neutral on whether that's a benefit or not, because a lot of the time we take that waste material and then we react it again to basically double dip on nuclear material for those reactions. Okay, and then finally, determining the age of a wooden beam from a sunken ship is an example of a beneficial use of radioactive nuclides, which really means radioactive isotopes. Another thing you may notice about part A is that typically it goes in order, the same order that I have taught on the YouTube channel. The nuclear stuff typically comes at the end. Redox is towards the end. Right? Redox was 25. Acid base was 27. Kinetics was 23 and 24. And then we have reactions, some bonding units, a few things on gases. They kind of go in order, which can sort of help you to answer the questions to make sure, like I was saying over here with this question, the anox and the red cat, if they just put in like atomic number, you would know this should not be the answer, because atomic number should be the answers to the first few questions of part A, not the end of part A. It can be, though. That's just like a gentle statement, not at all a blanket statement, take it to the bank type statement. It's a starting point for when you need to guess. So yeah, Lewis structures are just drawings. Polyatomic ions don't make any sense. And a homogeneous mixture also doesn't make any sense. Okay, and that is part A. Moving into part B, oh, we love these bright line questions, right? Because they're so stressful because you have to line things up. Okay, so part B is, well, the first part of part B at least is still multiple choice, which is fantastic because the right answer is looking at you. You just have to look back at it. Given the bright line spectrum of 4 elements and the spectrum of a mixture formed from these elements, which 2 elements are present in the mixture? We are looking to line up the lines for said elements. Wow. Okay. So the letters are weird because they don't want it to be like B for boron or, C for carbon. That's why they're Q and E and G, whatever. They don't want you to confuse them with real elements or go to the periodic table looking for an answer. But we know that there should only be 2 because the question says which 2 elements are present in the mixture, which is a fantastic start. Okay, so just running through this. A has 2 lines right there. I would honestly take like my reference table and line it up and see how it fits. I would draw all over this question. But these 1, 2, 3, 4 are kind of matching these 1, 2, 3, 4 down here, which I like. So I think those 2 belong to A. I think that belongs to A. This line here, I think, belongs to A. These 2, I believe, are A. That is also A. There's A there. This is A, and then this is A, right? And then Q would match this line here, right? E doesn't have a line there, and G doesn't have a line there, and neither does A. So this one kind of has to line up with Q. Let's look at the rest. These 2 belonged to A. Those 4 belong to A. Oh, this one here. Q. This one is Q, and I think that one's Q. So that is my answer, A and Q. You just line them up. Use the other papers on your table to make sure that you're lining them up properly. Those are not my favorite questions by any means. 32. What is the approximate mass of an atom that has 10 electrons, 10 protons, and 9 neutrons? When it comes to mass, we don't talk about electrons because they're so tiny that they don't count. It's like if you were counting the weight of a grocery bag and then you put a tiny grain of rice in there. You don't change the mass of the entire grocery bag based on 1 grain of rice. That's the way electrons are. So we're just going to look at these protons and neutrons because they are the meat of the atom's mass. They're the bulk of it. 10 plus 9 is going to give me the 19, and U stands for atomic mass units. That information is on table D at the front cover, like towards the end. 33. Which electron configuration represents the electrons of an atom in the excited state? Okay, so you should be noticing that these questions are like a little step up. You actually have to like apply this question a little bit. Here we're looking for an atom in the excited state. So the excited state is going to not be on the periodic table. The periodic table only contains ground state configurations. So, looking very diligently, 2881 is potassium. Where are we? Slide over. There we go. 2881. That is potassium. That's the ground state configuration. That's all they put on the periodic table. So that is the first piece. And then the second one that I wanted to rule out was... Oh, I shouldn't have circled that. Let's cross that out. 282 should be magnesium, right? Yeah, 282 is magnesium right here. So I don't want to choose that one because that's a ground state configuration. So I'm between 273 and 2892. Now, when it comes to electron configurations, ground or excited, it does not matter. You cannot overfill any of the orbits. So option 4 cannot happen. I'm going to tell you how you know how many fit. This 9 is too big. So let's go take a look at the periodic table. And I'm going to zoom out quite a bit here. Okay. The first shell of any atom can hold 2 electrons. And I know this because there are 2 elements in the first period of the periodic table, hydrogen and helium. 2 elements means I can hold 2 electrons in that first energy level. Then the second energy level can hold 8 because there are 8 elements from lithium to neon. Count them, there's 8. This periodic table was not organized like a knucklehead did it. It was designed very strategically. The third level can also hold 8. If you count from sodium to argon, you have 8 elements. You got 8 valence or 8 electrons in total fit in that third energy level. Then we jump all the way to 18. There is no option to have 9 in the third energy level. At that point, it's overfilled. The energy levels will never overfill because electrons repel each other. They will, on the other hand, underfill, and electrons kind of like underfilling because it gives them a little extra wiggle room and space because they are not near other electrons for like a hot minute. They repel each other, remember? So they will underfill, but they will never overfill. And when they underfill, what happens is that they have to jump up to higher levels. They can't jump down because jumping down would be overfilling. So this is going to be 1. Now, if we add up these numbers, that's 10, 12. This is an excited state of magnesium, in fact, because the 2, the 7, and the 3, add them up, you get 12. That is going to be the magnesium in an excited state. We did basically this question on the last test also, 34. These questions are kind of annoying because for the atomic mass questions, the answer legit is on the periodic table. Bromine is 79.90 is what the average comes to. So, like, if you wanted to, you could sit here and plug in all 4 of those answer choices to figure out which one gave you the correct answer. I don't recommend that. It takes up too much time. And it's not that hard to learn this one. So what you need to do is take the atomic mass and multiply it by the percent abundance, and then add that to the mass times the abundance of the next isotope. Now, percent is kind of a unit. 50.69 really means like 51 out of 100, more or less. It's a fraction. The percent is just a way that we can talk to each other about it and give it a nice number instead of it being like a number less than 1. So it really is a fraction. It means 51 out of 100, more or less. And that 49.31 is 49 out of 100. So when we go to manipulate it and do math with it, we have to put it back into that fraction form. We don't actually have to use a fraction, though. We can make a decimal equivalent. So we don't want to use options 1 and 2 because all it did was take that percent and plop it in there, and it's not a proper use of that data. What we want is for this to match straight across. The atomic mass times the abundance going across plus the mass times the abundance. So that is going to be choice 3. That's where your data lines up. Again, you could plug these into the calculator. You can kind of like know this and then go plug it in just to make sure that you picked the correct thing, which would not be a terrible use of your time. But doing all 4 of them straight up to try to figure out which one's correct, learn it. Okay, 35. What is a chemical name of the compound CuS? Okay, love this. Obviously, we're working with copper. That is Cu. S by itself is sulfide. Sulfate would be a polyatomic ion. It's the polyatomic ion SO4 with a -2 charge. And this baby has no oxygen, so it is not sulfate. It has to be sulfide. The question is it copper 1 or is it copper 2? You can uncrisscross this using the subscripts. Copper has the invisible 1 and sulfur has the invisible 1, right? So that would be copper +1 and sulfur -1. But sulfur doesn't like to be -1. Sulfur really likes to be -2. And copper can be +1, but it really likes to be +2. So that's what happened here. This was the copper 2 sulfide, and it was reduced down. If we look at the periodic table, whoops. Taking a look at sulfur's oxidation states. Come on, slide over. There we go. Sulfur, come on. I don't care what time it is. I don't care about the weather. I don't care about the Olympics. How do I make this go away? Oh my goodness. Go away, please. I don't care. Oh my goodness. Okay, sulfur. If you're in the chat box and you know how to make this go away, please help me out. Sulfur is not going to be plus anything. There we go. Ugh. And then it just opened Microsoft on the other side. Ay. Sulfur doesn't like to be -1. Sulfur will not be -1. It'll be -4. I'm sorry, -2 is what it'll do ionically because it's going to take the minus to bond to a metal. But it can be +4 and it can be +6, but typically that's going to be in a poly. Okay. Oof. Anybody else sleepy? 35. We're not even halfway through yet. Okay, 36. We have a reaction. Given the equation representing a reaction, what is the mass of nitrogen produced when 1 gram of hydrogen completely reacts with 15 grams of nitrogen oxide to produce 9 grams of H2O? What? Okay. This sounds like it's a stoichiometry question, but Regents Chemistry does not ask mass-to-mass stoichiometry. What is the mass of nitrogen produced when 1 gram of hydrogen completely reacts with 15 grams of NO to produce 9 grams of water? This is really a law of conservation question. And we love it. It's tricky though, especially if your teacher put you through the ringer on stoichiometry. If 16 grams of stuff goes into a reaction, 16 grams of stuff has to come out. So, if 9 of those grams were water, then the other 7 would have to be nitrogen. Again, that's a law of conservation question. I would say that honors students are most likely to get that one wrong, simply because it looks like it's a stoichiometry problem and it's kind of crazy. And then you do all the stoichiometry and you come back with something nuts. They don't ask mass-to-mass stoichiometry on the Regents exam. Moving on to 37, an atom of which element bonds to an atom of hydrogen to form the most polar bond? This is bend. Bend stands for bond, electro, I know this is one word, but negativity difference. If you take the electronegativities and you subtract them, you will find out if your bond is polar, non-polar, really, really polar, so polar it becomes ionic, blah, blah, blah. Here we're looking at all of the halogens. So you could also equate this to a periodic trends question if that's more so your speed. If we were to consider group 17, the halogens, we would have fluorine, chlorine, bromine, and iodine in order, just like this. Fluorine is a nonmetal and it's at the top of that group. It has the highest electronegativity. And iodine has the lowest electronegativity. So if we do a high number minus hydrogen, which I believe is 2.2, if not, it's 2.4, and carbon's the other one. Fluorine is 4.0. It's got the highest, so you're subtracting the same number from each of these. Again, you would use table S to determine the electronegativities. Or simply, you use a periodic table trend. Given the diagram representing a classification of matter, what type of matter are shown by X and Z? Interesting question. Okay, X must be substances because iron is an element, calcium carbonate is a compound, air and sodium chloride, aqueous specifically, are both mixtures. So this would have to be mixtures. And this would have to be something that encompasses elements and compounds, and that would be a substance or a pure substance. So X is a substance and Z is a mixture. Okay, 39, our first based on table blank question. 39, based on table G, which sample, when added to 100 grams of water and thoroughly stirred, produces a heterogeneous mixture at 20 degrees Celsius? For a heterogeneous mixture on table G, it must be a saturated solution. I talked about all of my issues with table G yesterday in that reference table stream. Specifically, we were talking about, let's see, what were the numbers? 20 degrees Celsius. And that's it. Ugh. Okay, we are looking at KCl, KI, which is all the way up here, and KI and KCl. Okay. Table G is based on dissolving in 100 grams of water. Occasionally, they'll change it in the question, and it'll be like 20 grams and 50 grams. And they're like really not that nice about it. If you're dissolving in 100 grams of water, you just read table G. If you're dissolving in 200 grams of water, you read the data point and then double it. If you're dissolving in 50 grams of water, you read the data point and chop it in half. So, 20 degrees Celsius, we are going to look at KCl. If I only put in 20 grams of anything, it would be this data point here, 20 grams at 20 degrees Celsius. And then 80 grams at 20 degrees Celsius. So KI is this line up here, all the way up there. So both of those data points for KI are going to be unsaturated, and therefore the mixtures would be homogeneous because everything is dissolving. Oops, that was not it. Come on. KI is unsaturated in both of those situations. And then KCl is going to be saturated at this data point here, because the line for KCl, I'm just going to sketch over a portion here. It's that line there. So this data point that I have circled is above the KCl line at 20 degrees Celsius right there. So that one would be heterogeneous because the solution is saturated. So there's stuff starting to accumulate at the bottom of that beaker. Number 40. How many milliliters of 1 molar hydrochloric acid must be diluted with water to make exactly 500 mils of a 0.1 molar hydrochloric acid? Okay. Here we go. We're going to use the titration equation here. It's also called the dilution equation. The question is how many milliliters? So we're looking for the volume. The molarity here is 1 molar. So 1 molar times an unknown volume is equal to 0.1 molar and 500 milliliters. Now, it doesn't matter what volume goes into this equation. You could do liters and liters or milliliters and milliliters. Just make sure they're the same. Here's my calculator. We didn't need a calculator till question 40. That's pretty good. Okay, so 500 times 0.1. I feel like I should know that that's 50. 1 molar times an unknown volume would just be volume, so my volume is 50 milliliters. The reason this is confusing is because you would do MV of the acid equals MV of the base, but they're the same thing. The question is diluting, which is why we don't love this question. We don't mind the question. It's just paired with this reference table we don't love. Okay. Moving right along, which two particle diagrams represent two phases of the same compound only? Yowzers. Okay. This one, choice A has double white right there, and then it has a black white. So this one is not the same compound. This is two different compounds. Actually, no, it's not two different compounds. One of them is a compound and the other one is a diatomic element. Okay. It has one diatomic element. This is the same thing. It's a compound. The compound is the black bonded to the white, and then the one diatomic element is the double white. So can't be those. Choice B is the black-white bonded, and D is the black-white bonded. Those are the same compound. This choice B happens to be a gas, and choice D happens to be a solid. So they are two different phases of the same thing. (42) A sample of KCl is dissolved in water to form aqueous KCl. When the water in the KCl aqueous is completely evaporated, the KCl solid remains. Which statement describes a property of the KCl after the water has evaporated? This is interesting. Okay. It's choice 3. The melting point is unchanged. KCl does not just become a molecular compound by being dissolved in water and then not being dissolved in water. A molecular compound is a compound that has covalent bonds. So no bonds were broken and no bonds were formed here. So no, it's not a molecular compound. Then next, the molar mass of KCl decreases. It started out as KCl and then it became aqueous KCl and then it was KCl again. K and Cl is equal to K and Cl. It's just done. And then that it conducts an electrical current. It will not conduct an electrical current in the solid phase because it's ionic. It will conduct if it is aqueous. We talked about that earlier, the mobile ions. But it will also conduct if it has, if it's molten. So if the KCl had been melted down, then it would conduct an electrical current. But the melting point is not changing here. Melting and dissolving are not the same thing. There's a whole video on dissolving if you need it. Okay, which statement describes ice and water in a stoppered flask at 0 degrees Celsius at equilibrium? Ooh, okay, this is phase equilibrium. Again, video on this. Phase equilibrium means that the rate of the endothermic phase change is equal to the rate of the exothermic phase change. So at 0 degrees Celsius, water is going to be sitting at its melting / freezing point, which means you will have a little ice cube of water, and it will be in a puddle, and it will be melting at the same rate that it is freezing, although it's going to be a particle like super close to the ice cube. So the rate of melting has to be equal to the rate of freezing. That's what makes it equilibrium. If one rate is faster than the other, then it is either actively melting or actively freezing. And the mass has nothing to do with phase equilibrium. So you can have a phase equilibrium during a phase change. You can also have a solution equilibrium if you have a saturated solution. Some of your undissolved particles sitting at the bottom of the container will start to dissolve, while some of your dissolved particles will undissolve and sink to the bottom of the container. Question 44, Le Chatelier's principles. There's a video on this. Given the equation representing a system at equilibrium in a sealed, rigid container, when heat is added to the system, the concentration of nitrogen does what? Okay. This reaction, currently, as it is written, the forward reaction from left to right, is endothermic. I know this is endothermic because heat is being added. It is a reactant. So this is endo. Endothermic reactions are trying to absorb heat. They're like, ooh, give me heat. Gimme, gimme, gimme. So if we have this reaction trying to absorb heat and we add a bunch of heat, this reaction's like, heck yeah, I'm excited. So the endothermic reaction is going to be happy here. The exothermic reaction is trying to get rid of heat. So the exothermic reaction is like, ugh, this is not happy. I don't like this. So this reaction will shift to kind of use all of that energy that the endothermic reaction needs to try to like use it up. So it'll shift to the right. Now, that's not the answer because it's not an answer choice. If we are shifting to the right, that means that the concentration of the nitrogen is going to decrease because we're going to use it up. And the concentration of the nitric oxide, or the nitrogen oxide, rather, is going to increase because we're going in that direction. We're shifting to the right. So we're going to use up the nitrogen, but we are going to increase the amount of the NO2 because we're shifting this way. So this side has to get used up and this side's going to increase. Okay. This, I would argue, is the 100 breaker. This is the question that is going to get honors kids flustered. This is the question that the kids who have been struggling all year, you're going to look at this and be like, wait, what? Can we go back to protons, please? This is I haven't even looked at the rest of the test. I would argue this is the hardest question. Not just because it's Le Chatelier's principles, but because you have to talk about two different things at the same time. Okay, 45. The potential energy diagram for the reaction. Which numbered interval represents the activation energy? Beautiful. Okay, activation energy of the reaction is the distance from the reactants to the activated complex. It is how much energy you need to start the reaction, so that would be choice 1. Choice 2 here is the energy of the activated complex. 3, the distance or the difference between the reactants and the products would be delta H. And then choice 4 is just the potential energy of the products. 46. Given the formula representing a compound, what is the name? Okay, obviously this is a pentane because we have 1, 2, 3, 4, 5 carbons and they're all single bonds. If we have all carbons, or rather 5 carbons, let's go check out those organic tables. 5 carbons, we're looking at pent. Right, we got 5 carbons, so we're looking at pentane. And then we have all single bonds, like this right here. So this is not pentene. It is a pentane. The question is it 2-chloropentane or is it a 4-chloropentane? So the strategy here is to number the carbons forward and backwards. 1, 2, 3, 4, 5 on the pink. 1, 2, 3, 4, 5 on the green. The reason we number it forward and backwards is because atoms and molecules in the real world are flipping and moving around in space. They are constantly topsy-turvy moving, and we just happen to grab a snapshot of this molecule. This molecule, if I'm looking at it from this side of the paper, somebody who's sitting on the other side of my desk and looking at it from this side of the paper, I am seeing the pink, that person is seeing the green. Okay, so we number it both ways to ensure that no matter how you look at the molecule, we come up with the same answer. We want that address or the number identifying where the substituent is, where the little dangly thing hanging off of the main chain is. We have to assign that the lowest number possible. And when we have multiple things, we add up all the numbers for one set, add up all the numbers for the second set, and whichever one's going to give us the lowest is the option that we choose. So in this case, it is going to be 2-chloropentane. The green is going to win that battle because the green system tells us that that chlorine is on carbon 2, which is lower than 4. 47, which is a saturated organic compound. The saturated organic compound is full of hydrogens. Saturated solutions are full of solute. Saturated organic compounds are full of hydrogens. So we are looking for which of these is an alkane. We have that formula there on table Q. Alkanes, you take the number of carbons, double it, and add 2, and that will tell you if it's an alkane or not. A simple alkane, I guess. So C2H2 is not fitting. C2H4 is not fitting. C3H4 is not fitting, but C3H8 is fitting. And guess what? That is propane, which we have seen like 4 times in this test already. For question 48, the compounds CH3, CH2, CH2OH, and CH3O, CH2, CH3 have different blank. Okay. They each have 3 carbons, so no, they have the same number of carbons. They each have 8 hydrogens, right? 3, 4, 5, 6, 7, 8. Yes, they each have 8 hydrogens. The answer is functional groups. They each have 1 oxygen. So considering that they have the same number of everything, they have to have the same mass. If we look here, this first one has the OH, which is going to make it an alcohol. Right here. And this one has that O trapped in the middle of the carbon chain, which is going to make it an ether right below it on the reference table. So they have different functional groups. When it comes down to it, the alcohol is going to have a better dipole moment because the oxygen is on the end, pulling a lot of electron density over there, where in the ether it's like kind of in the middle. So they'll also have different chemical properties, and that's because they have a different structure. Ooh, voltaic cell is my favorite. Call me crazy. The diagram and ionic equation below represent an operating voltaic cell. Which phrase describes the direction of electron flow in this cell? Okay, I love it. In a voltaic cell, they are always, always, always going to move from anode to cathode. And they are also going to move over there. They go from anode to cathode, but they are also going to go from loser to gainer. One metal is going to lose electrons and push them to the gainer. And the question is, who is losing and who is gaining? There's a few ways to figure this out. I'm going to work from hardest to easiest. So in this case, we have magnesium metal becoming a magnesium ion. Magnesium has to lose electrons in order to become an ion. In order to do this, magnesium needs to lose. If we have nickel with a +2 becoming a nickel atom, it has to gain electrons. So they're going to go from magnesium to nickel. Electrons do not move through the salt bridge. The salt bridge is for ions. It's these ions that are swimming around in the pools. They have to move through the wire. So they're going to go from magnesium to nickel. Now, the other way to figure this out is with table J, which if you don't love redox, you'll probably like this better. Looking at table J, we have to find the two metals in question, which are magnesium and nickel. Whichever one is on top is the loser / the anode, and whichever one is on the bottom is the gainer / the cathode. Okay, so on table J, anodes at the top, cathodes at the bottom, losers at the top, gainers at the bottom. The flow is from anode to cathode. I know how much redox is like a memorizing the tricks type of thing. I 100% understand that, which is why I anticipate that you would like table J, because it helps you out with things like this. This way you don't have to decipher the chemical equation, especially when you're getting toward the end of the test and your brain is wearing out. Honestly, when I was a student, I would take these tests backwards. I would start at question 85 and I would work my way to question 1 because I felt like the back of the test was much harder than the beginning of the test, and I wanted my fresh brain to look at the tougher questions, and I wanted my tired brain to look at the easier questions. But that's me. Other people want to do the easy stuff first and get like the confidence boost. So you make sure that you take the test whichever way works for you. But if you do it backwards, be careful that all of your answers go in the right place. Okay, 50. Given the equation representing a reaction at equilibrium, according to one acid base theory, which pair are H+ donors? Whoop. Okay, we have to look at the before and after. So that's really all a chemical reaction is a before and after. We have a before, we have a chemical reaction, and we have the after. NH3 is going to become NH4, and it's going to gain a proton. So it is going to accept the proton. And if it is going to accept the proton, bases accept, acids donate. That's what BAD stands for. The bases accept. NH3 is the base. And this one is going to accept, which would make it the conjugate acid. H2O in this case, because it's not the base, it would have to be the acid. It is going to become hydroxide. In that case, it is losing or donating the proton. So that would make it the conjugate base. So the donor is going, and this is an equilibrium, so it's going forward and backwards. In this case, it's water and NH4. And if, what was it, 44? If that wasn't the 100 breaker, then this is. Because again, it's asking you about two things. It's asking about NH4 and about water. But it's asking which ones are donating, and the way they're able to ask this is because it's in equilibrium. It goes forward and back. Okay. That was the end of the multiple choice. I suggest you pause, go stretch, get a drink of water, shake your brain a little bit. And then come back for part B2, which is where the free response starts up. And we are now going to be working with the answer booklet. So if you are interested in printing that, I would consider it. Okay, for question 51, it says identify a metal from table J that is less active than silver. And this has absolutely no context. They just want something that's less active than silver. There is only one option that is less active than silver, looking at table J, and that is AU. It tells you right here that it's least active. So for 51, we are going to say AU. And my recommendation is to not translate that into something else. I would say if table J says AU, then you say AU. You know why? Because it's question 51. And at this point, your brain is getting tired. Don't write gold. Just say AU. As I discussed in the last live stream, students have a tendency to over-explain themselves and talk themselves into a wrong answer, or you just give one tiny little blip of information wrong, and then it makes your entire answer wrong. And like, whoever's grading it probably knows what you're talking about, but we can't like say beyond a reasonable doubt that you absolutely know what you're talking about. So if it's AU and you put, I don't know, something weird, we can't give you credit. Just give us the obvious answer and don't overdo it. Okay. 52, 53, and 54 all kind of go together. It says fluorine, chlorine, bromine, and iodine are located in group 17 and are called halogens. Great, thanks. State in terms of electrons why these halogens have similar chemical properties. Okay, nowhere on this test does it say you have to answer in a complete sentence. That's not part of this chemistry test, so don't worry about that. There are a few things that you could write here. My answer choice is same number of valence electrons. Done. Each has 7 valence electrons would also work, but make sure your handwriting is beautiful and that your 7 doesn't look like a 1 or it doesn't look like a 9 or it doesn't look like you wrote all of the numbers in one digit and we have no idea what you're talking about. So you have to say something about electrons when it says state in terms of electrons. Your answer basically has to include the term electron, so make sure that gets in there. And I would say those are like the only 2 acceptable answers. Okay, next says compare the radius of a chlorine atom to the radius of a Cl- ion. Okay, so this is the opposite of MELPS. MELPS stands for metals, electrons lose positive and smaller. When metals lose electrons, they become positive ions, which are smaller than the atoms from which they came. That's MELPS. MELPS helps. Nonmetals do the opposite. Nonmetals, when they gain electrons, the electron comes into the valence shell, and that all those extra electron repulsions are going from the added electron are going to make the atom expand out a little bit bigger. So for 53, the chlorine ion is going to be larger than the chlorine atom. They don't ask why, so don't give them an explanation, because if you explain it wrong, then your answer is wrong. Cl, where am I? Over here. Come on, baby. Cl minus is larger than Cl atom. That's an acceptable answer. They give you 3 lines. There's no reason to use all 3 lines. Again, keep your answers as simple as possible so that you are not talking yourself into a wrong answer. I would hate to see that happen to you. 54. In the space in your answer booklet, draw a Lewis dot diagram for an atom of fluorine in the ground state. Fluorine is F. If you don't know that, look it up on table S. Fluorine has 7 valence electrons, which we know because it says so right there, that little 7. When we draw a Lewis structure for fluorine, we have to draw the F, and then we need 7 dots, kind of as if they were on sides of an imaginary box. No more than 2 dots per side. It doesn't matter which side gets left over with the single one. It could be the top, bottom, left, or right, but that's the acceptable answer. They have to kind of fit on the sides of an imaginary box, because when we draw these Lewis structures, and when you get into like higher level chemistry, they get expanded out kind of like in graph paper format, kind of. It's like they're only to the left or only top and bottom. It's exceptionally rare that they go out diagonally. So it's going to look something like this. A sample of helium in a sealed rigid container at 240 Kelvin and 120 kPa. The temperature is increased to 360. From where? Where did it start? Oh, 240. Where is my brain? Okay, 55. State the number of significant figures to which the pressure is expressed. This is interesting because they are not telling you the pressure is blank and the temperature is blank. This one's the pressure. kPa is kilopascals. That measures pressure. So we're looking at 120 with the decimal in the back. Because the decimal is present, we will approach this number from the Pacific side. We will count the first non-zero number and everything that comes after it, no matter what. So that will give us 3 significant figures. Okay, 56 says determine the pressure of helium at 360. So this is a combined gas law question, but it's not quite a combined gas law question. So if we go look at the reference table, the combined gas law, I gotta rotate back. I don't know how to get Cami to do this nicely. The combined gas law, where are you? Right here. Has pressure, volume, and temperature. In this particular example, our volume is held constant. And I know this because it says that we are in a sealed rigid cylinder. A rigid cylinder you can think of like a thermos. It's that, like, it's not like a plastic water bottle where you can squeeze it and apply pressure. It doesn't have like the syringe or the movable piston to kind of like change the volume. The volume is set. So let's just say that that volume is 1 liter. It's going to be 1 liter on both sides of this equivalency, this equation. I don't know the math terms. It's the same on both sides. And because it's the same on both sides, you can plug in any number you want. You can make it 1, you can make it 55, whatever floats your boat. Or you could just make it invisible because it's the same on both sides, so we don't need it. So really, this is P over T, which I think is Gay-Lussac's law. It doesn't really matter because it's just he got credit for doing, they all got credit for doing basically nothing. The volumes are held constant because we are in a rigid container. And my original pressure was that 120. We have 120 kilopascals over the original temperature of 240. And then this is going to be equal to some new pressure over the new temperature of 360. 180 should be the answer. You cross multiply and solve for P. 120 times 360 is 43,200. Divide that by the 240. And yes, it is 180 kilopascals. Technically, there should be a decimal behind the 0 in there to give it 3 sig figs because all of our measurements had 3 sig figs. But this question, and nowhere on the directions does it say that we have to answer all of our math questions to the correct number of significant figures, so 180 would also be correct. Okay, then it says show a numerical setup, which means you don't have to solve it, but it's asking you to convert 120 kilopascals to atmospheres. To do that, you would use the information on table A. 101.3 kilopascals is equal to 1 atmosphere, and you just set it up like it's a ratio. So 120 kilopascals is equal to an X number of atmospheres, where 101.3 kilopascals is equal to 1 atmosphere. And I didn't write that in the answer book, but that's what it should be. 120 kilopascals is equal to X atmospheres as 101.3 kilopascals is equal to 1 atmosphere. Any mathematical equivalent iteration of that answer is going to be correct. (120 over 101.3). That would work. Whatever comes out equivalent. Ooh, okay. The table and graph below show information about 5 aldehydes. So we're talking about successive aldehydes because each time we're adding 1 carbon. Methanal, ethanal, propanal, butanal, and pentanal. And our molar mass is increasing. And the boiling point is also increasing. And it's kind of increasing in like almost a straight line here. But one of the data points is missing from the graph. 30, 44, 58. Oh, butanal is missing. Okay. Based on the graph, determine the boiling point of butanal at standard pressure. Okay. You don't have a ruler to take this test, but you do have a reference table, and I would just use that to draw a line, right? It's a pretty predictable line here. Connect the dots. Butanal is 72.1. The bold lines are 10s, but the gray lines in the middle are 5, so 72 would be right about there-ish. 72 for the molar mass. And then I'm going to slide over on the boiling point, and I'm going to come up with about 350. The dog is here to cry for DINNER. Where is it? Yes, we want to take a look at this. We are doing, what question, 58? Okay, so just looking at this, just so you're not like paranoid about it, it says right here, question 58, it says allow 1 credit for any value between 340 and 360. So there's a really huge range. Like you could be off by 19 Kelvin and still get the correct answer, depending on what the actual true answer is. All of these questions that have you interpret things like this, they give you an appropriate range that your answer is allowed to fall within. And as long as you fall within that range, your answer is considered correct. So my 350 will work just fine. Okay, question 59. Determine the mass of 3 moles of propanol using the molar mass given in the table. A molar mass is the gram of 1 mole, so 3 moles must be that same thing times 3. We could have also set this up as a ratio if you are interested in that. 58, well, let's do it like the way you should. Ooh, sorry. 3 moles is equal to X grams, as 1 mole is equal to 58.1 grams. Cross multiply. 58.1 times 3 is 174.3. 174 is technically the correct answer for like significant figures purposes, but again, we're not talking significant figures. I don't understand why we're going out to 6 things here, but okay. That's what they're doing. I'm telling you, the Regents board is very strange. Okay, moving on to question 60. You guys, we only have 20 left. A 100 milliliter sample of liquid water is heated in a flask to boiling at 1 atmosphere. As the water boils, some liquid water changes phase to water vapor. The equation below represents this change. Describe the change in potential energy of the water molecules that vaporize during boiling. They have more energy now. Is that what it's looking for? Oh, yeah, that's it. Okay, so writing the simplest answer that we can so that we don't talk ourselves into a wrong answer. Vapor has more potential energy than liquid water. Now, if I were a teacher in a classroom and I was just giving this test to my students and they wrote PE for potential energy, I would accept it as a correct answer. This is allowing for PE. I don't know if you can see that. I know it's super tiny. I don't know how to zoom in on this. Can I just do this? Oop. Yeah, there we go. Okay, so for question 60, it is accepting PE in place of the term potential energy. I wouldn't rely on that. I would just write out potential energy. This way you can tell the grader, like, hey, it is potential energy I'm talking about. It's just not just random stuff. 61, compare the entropy of liquid water to the gas that is formed. Vapor has more entropy. Liquid has less entropy. That's another acceptable answer. You could also say, like, the vapor is more disorderly because that's what entropy is. Are they accepting that? Yes. Random, disordered. Those also qualify. Woof. Okay, 62. We have some math. Determine the mass of liquid water that vaporizes if 7,700 joules of energy is absorbed by H2O at 100 Celsius. This is going to be Q equals mHV. The reason I know it's HV is because we are transitioning from a liquid to a gas. We'd have to use the heat of vaporization for that. So we have to determine the mass. So I'm solving for M. Q is heat. So that's the 7,700 is going to be equal to some unknown mass times heat of vaporization. Heat of vaporization is right here on table B for water. There was one year they did ammonia and everybody freaked out. It's 2260. That's the heat of vaporization for water. So that's what I'm going to plug in for HV right there. To get M by itself, you divide both sides by the 2260. And I'm getting 3.407. And that would be my answer, 3.407 grams. And yes, my answer would work. The thing is that the calculator goes on forever and ever and ever. It says any value between 3.4 and 3.41. So if you wrote all the digits in the calculator, technically you would be correct, but you would also look like a nincompoop. So just take a look at rounding and variables and sig figs, just so that your answer comes in looking proper and that you don't look like a crazy person. Okay. I never know how to pronounce this. Tritium. H3 is a radioisotope. State the number of neutrons in an atom of tritium. Okay, this is not bad. Just because I can't say it doesn't mean that it's impossible. H3 is what we're talking about. All hydrogens have one proton because they're number 1 on the periodic table. So the 3 is the sum of the protons and the neutrons. Remember like 2 hours ago when I was talking about how this test has so much isotopes on it? The protons plus the neutrons is equal to 3, but I know that the protons is equal to 1. So 1 plus n is equal to 3. The magic number of neutrons here would have to be 2. Don't write 2 neutrons when you do this. Just write 2. Because you'll flub it up and you'll write 2 protons. And then you get the answer wrong. Give only what they ask for, nothing else. Excuse me. Okay, it says complete the nuclear equation in your answer booklet for the decay of tritium by writing a notation for the missing nuclide. Okay, so I'm going to write it here so we have it nice and big. It's 3/1h plus 0/-1e. Whoops, that's not plus. That's yielding. Yields plus blank, okay? When we do this, we want to treat it like 2 little baby algebra problems. 3 equals 0 plus mystery number. Mystery number has to be 3, meaning I need a 3 up top. And on the bottom, I have 1 is equal to -1 plus mystery number. Mystery number would have to be 2, right? -1 plus 2. Yeah, it's 1. That doesn't make sense. It's 2. Why did I just write 1? 2 minus 1 is equal to 1. Yes. Okay. Because this is a 2, that means that this is helium. The 2 on the bottom is the atomic number, i.e. the number of protons. So if I go and look up number 2 on the periodic table, I'm not even going to rotate it. That bold 2 right there is the atomic number of helium, telling us that this is, that this is 3/2 helium. Helium will also very often come as a 4 over 2, so be careful of that. It is specifically 3 over 2 helium. And I would write it like that first choice there. You see that one? I would not write He3 or helium-3 or 3 helium because that doesn't fit in that equation format very nicely. And I would be afraid that in future years they won't accept all those crazy answers because they specifically ask you to put it in the equation. Okay, 65. Based on table N, identify a nuclide that has the same decay mode as tritium but has a longer half-life. Okay, so we're going to table N. Because it specifically told us to go to table N, which is fantastic because we love when that happens. And right here is tritium, hydrogen 3. And it is a B negative. It is a standard beta decay. We need something that has a beta as the option, but it has a longer half-life than hydrogen right there. So beta, but longer than 12 years. So, and it's specifically beta negative. So carbon 14 would work. Cobalt 60 would not because it's too short. Cesium 137 works. Strontium's too short. Potassium just makes it. Krypton is too short. Nitrogen's too short. Phosphorus too short. Strontium 90 will work. Technetium will work. And that's it. So those are the only 5 answer choices. I would pick, personally, the carbon 14. And that would be it, 14C. And I would write 14C because that's what it lists on table N. That's why I would write it specifically that way. Okay, now we're into part C, and part C is where we get those little blurbs. They're usually like 4 or 5 sentences, and it's going to give us some like backstory to something that we probably don't care about. But you need to read them because they hide information in there that can help you answer the question. So even though you have to read, just read it. It's not so bad. I know you don't care. This is why I do part C first, because I don't care about it, but my brain is sharpest at the start. So that was just me. Okay, phosphorus combines with oxygen to form an oxide that reacts with water to produce phosphoric acid, which is an important industrial compound used to produce fertilizers. An unbalanced equation for the production of phosphoric acid is shown below. Okay, 66 tells us we need to balance. Okay, we can do this. When I balance stuff, I have like a whole video on it. I do this whole method where I list everything. I do it in columns. I make it work. At this point in the year, I think you probably don't need a whole method, but if you do, go back and watch that video because it's pretty good and it gives you a good process. I have 4 phosphoruses over on this side. Let's zoom in a bit here. I have 4 phosphoruses on the product side, so I'm going to put 4 on the reactant side right there. That gives me 4 times 4 is 16 oxygens in total. But my oxygens on this reactant side are split, so I don't really want to fuss with them right now. I would rather take a look at the hydrogens. Right now I have 12 hydrogens on my reactant side, so to get 12, I have 12 on the product side. So to get 12 on the reactant side, I'll put a 6 right there. 6 times that 2 will give me the 12 hydrogens. The oxygen, though, is now this 10 plus this 6, where 4 times the 4 will give me those 16 oxygens there. So that's all I needed. It is 1 or blank, then 6, then 4. Those are the coefficients. Let me check the key to make sure. Allow credit even if the coefficient for 1 is in front. Yes, I did that. That is fine. 67 says write the empirical formula of the solid reactant in that equation. The solid reactant is P4O10, and the empirical formula is the most reduced and simplest version of that formula. So P4O10 would be reduced down to P2O5, and that's as simple as you could get it. Question 68 says, show a numerical setup for calculating the percent composition by mass of phosphorus. Okay, so they're giving you the formula mass of the whole thing, and you need to figure out how much phosphorus is in here. So it would be the total of all the phosphorus over the 283.89. The issue is that you need a numerical setup, meaning that this total phosphorus, you have to come up with a number for that. So we're going to look up phosphorus on the periodic table and find out how much it is, and then multiply that mass by 4 because I have 4 phosphoruses. Okay, so phosphorus is right there, 30.97. I'm going to multiply that by 4, and I'm getting 123.88. 123.88, and I'm going to divide that by the total of 283.89. I'm going to multiply that by 100 because it's a percent composition. Yeah, so you can see right here that they allowed you to just do 4 times, which I didn't even think of. I guess that makes sense. 4 times the mass of a phosphorus. They took the phosphorus rounded to 100. Rounded to the nearest whole number. They allowed you to do the math, which is what I did, 123.88. I don't know what this is. Oh, they've already multiplied it by 100 in the numerator, which is silly, but okay. They did that part in the numerator of their thing. Okay. Strange. Okay, and then for question 69 rather, determine the oxidation state of phosphorus in phosphoric acid. I love oxidation states, honestly. I use what I call a QCT chart, quantity, charge, and total. Phosphoric acid, it told us that it forms phosphoric acid, so it's telling us that the formula is H3PO4. So I list all of my elements, and then I do my quantities. I have 3 hydrogens, 1 phosphorus, and 4 oxygens. And then I check out charges. In an acid, hydrogen is going to have a +1 charge. Phosphorus is the thing I'm looking for, so I'm going to leave that blank, but I'm not going to do that because I don't want it to look like 0. Let me do this. And then oxygen is always -2. Multiplying across all of my hydrogens will total +3. My phosphorus is a mystery. And then oxygen has a -8 because it's 4 of them, each at -2. And I need my total to come out to 0 because phosphoric acid is a neutral compound. So the mystery number that goes in this blue box would have to be +5. +3 plus +5 minus 8 will give us 0. Because I only have 1 phosphorus, the charge of a single phosphorus is also +5. So that is the answer. It's +5. +5. 10 left, people. Woo! Calcium oxide, also known as lime, is an important industrial chemical. Lime can be obtained by heating limestone, which is mainly calcium carbonate, CaCO3. An equation representing the reaction for the production of lime is shown below. State the solubility of limestone in water. Limestone is calcium carbonate, CaCO3. So the solubility is either going to be insoluble or soluble. We're going to go take a look at the solubility table, which I believe is F. There we go. There's table F. We love table F. Table F is actually a combination of two tables, and I talked about this in the reference table live stream, so definitely head back and take a look at that if you haven't. These inner two columns represent stuff that does not dissolve. If your compound falls in the circle, then it is something that is insoluble. And carbonates do not like to dissolve. And calcium is not an ion that can get carbonate out of the circle. Calcium is not a member of group 1, and it is not ammonium. So calcium carbonate is insoluble in water. So the answer here is just insoluble. Then question 71. State the evidence from the equation for the reaction that the reaction to form lime is endothermic. And we've already done one of these on this test, so whoever put this test together had a favoritism, I would say, towards endothermic and isotopes. Endothermic, because heat is entering the reaction. Heat is a reactant. Heat is required for the reaction. Something to that effect. I would just say heat is a reactant. And that would be all. That's all she wrote. It's a reactant. It's on the left side of the equation, or heat must be added. Works for me. That's beautiful. 72. Identify the noble gas that has atoms in the ground state with the same electron configuration as calcium in the ground state in the calcium carbonate. Youch. That's a tough question. Okay, so calcium carbonate is in an ionic bond, or rather calcium in the calcium carbonate is in an ionic bond, and it has a +2 charge. And if we go take a look at the periodic table, and we're going to zoom out so we can see the whole thing at once. Calcium is over here, number 20. If calcium loses 2 electrons, it goes back 2 places on the periodic table. So it would wind up looking like argon. AR. Another way to take a look at that is that calcium started out with 20 electrons and it lost 2, so now it has 18 and it looks like argon. You could do it mathematically, or you could do it with like your little finger skip jumping on the periodic table, which is my favorite way to do it. But either way will work. State the type of chemical bonding in calcium oxide. Calcium oxide is a metal bonded to a nonmetal, and obviously they have to transfer electrons in order to do that, which makes this an ionic bond. Number 74, during a lab activity, a student places 20 milliliters of HCl of an unknown concentration into a flask. The solution is titrated with 0.10 molar KOH until the HCl is exactly neutralized. At the end of the titration, the volume of KOH is added to 42 milliliters. During the lab activity, appropriate safety equipment is used and safety procedures were followed. Compare the number of moles of H+ ions to the moles of OH- ions in the titration mixture when the HCl has exactly neutralized the KOH. The key term in this question is that it's exactly neutralized. If it is exactly neutralized, you have exactly the same number of hydrogen ions as you have hydroxide ions. And if you have the same number of ions, you have the same number of moles. That's what makes it neutral. That's why water is neutral. Water is neutral because the formula is HOH or H2O. So that is what the answer is. Yeah, they're equal. That's what I said. They are accepting a 1-to-1 ratio, though, in case you're a ratio kid. 75, determine the concentration of HCl in the solution using the titration data. And this is one of those times where it's best to read the question so that you know what you're doing. Because it's very easy to skip over this and be like, oh, I don't want to read. It's the end of the test. I'm getting tired. Don't. What I don't love about this test is, again, they're making you use the same equation that we've already used before. I would argue this is a sloppy Regents exam. I don't love it. But still, you would use the titration equation here. The molarity of the acid is unknown. That's what we're looking for. Concentration is molarity. First off, this is acid and this is base. So we have an unknown molarity of acid, and we're going to multiply that by its volume of 20 milliliters. Then we have the molarity of the base is 0.10. And we use 42 mils of that. So 0.10 times 42 would be 4.2, right? 0.10 times 42 equals 4.2. Yes, we have 20 m is equal to 4.2. Divide by 20 on both sides. And the molarity should be 0.21. The reason for this is because we're titrating HCl with KOH, which is a 1-to-1. For every one hydrogen ion, you get one hydroxide ion. And my answer was correct, so I did the math right. Moving on to an organic chunk. A scientific sampling instrument landed on a comet. Okay. 4 of the organic compounds detected on the comet were methyl isocyanate. They give you scary things on purpose. Don't let them trip you up. Propanone, propanal, and ethanamide. The structural formula for methyl isocyanate is shown below. Identify the element in the 4 compounds that makes them organic. Tell me why we just read chemicals that I even couldn't pronounce. And then this question is, what's the element that makes it organic? You know this, it's carbon. I'm telling you, they give you these questions on purpose to stress you out. Don't let the part C's trip you up. Don't do it. 77. Write the names of the 2 organic compounds detected on the comet that are isomers of each other. Okay, this one I think is an interesting question. I don't love it. Okay. Methyl isocyanate is this one. Then we have propanone and propanal. And when we are looking at the reference tables, I really hope that your chemistry teacher made the point that aldehydes and ketones are almost the same thing. I want you to look at this very closely. Aldehydes and ketones have only one teeny weeny difference. Oop, I don't know what I just did. Aldehydes have that double bonded oxygen. Ketones have a double bonded oxygen. But there is just one difference between an aldehyde and a ketone. And the aldehyde must absolutely has to have the double bonded oxygen on carbon 1. It has to be at the end of the molecule. That's what makes it an aldehyde. The ketone is going to have that double bonded oxygen anywhere but the end. Okay? So that's the only difference. It's just the placement of that double bonded oxygen. Now, if we look back at the methyl isocyanate, we have 2 carbons, which we would have in this ethanamide, right? Because F stands for 2 carbons. But we're talking about an amide. And if we go and look at the amide, this would be something like this. We have propanamide right there. If I want ethanamide, I would have 2 carbons. I'd have the double bonded O, and then I would have an NH2, and I would have, that looks like a hydrogen. Oh, don't do that. I would have a hydrogen here, and here, and here, right? So I'd have C2H, 1, 2, 3, 4, 5, and a single O, and a single nitrogen. C2H5ON. C2H3ON. You see how I'm short on the hydrogens? So this one has to be the propanone and the propanal. Now, the propanal does not have a number on the name of the molecule, and that's confusing. But the reason is because, the propanone doesn't have a number. And the reason is because propanone only has 3 carbons, and the double bond has to go not on the end. So propanone will always, always, always have that double bonded oxygen on the center. And because it's in the center and all of the other chemists know it's in the center, they don't put a number. Because they're like, ugh, everybody knows this. Even though some of us are new at this, they get annoying. Okay, so that's why there's no number. And that's part of the reason why they chose this specifically. It was a little bit to confuse you. Sometimes they're nice and sometimes they're mean. And this is a lot of reading and a lot of stuff for the last few questions. Okay. During a lab activity, appropriate safety equipment is used and safety procedures are followed. A student tests samples of 4 different metals using 0.20 molar aqueous ion solutions of the same 4 metals. The student uses a 24 well plate as the reaction container for the different metal and solution combinations. Before placing a metal strip in each solution, a student cleans the surface of the metal strip with sandpaper to make sure there's no oxides on it. 24 well plate diagram below shows the setup and results of the investigation. In a vertical column, the metal strips are all the same metal. For a horizontal row, all of the solutions contain the same metal ion. Okay. Using the results in the student's investigation, state evidence that zinc metal is more active than copper metal. Okay. So in this case, we are being asked to look at zinc compared to copper. Zinc is this, and copper is this. Copper has no change in any of its setups, but zinc has a change. It has a, it reacts in 2 of these situations, right? So right there, that is telling us zinc had 2 reactions out of a possible 4, and copper did not react at all. So for 78, I would say, of the 4 reactions possible, copper reacted 0 times, and zinc reacted twice. Boom. Okay, 79, compare the number of electrons lost by magnesium placed in a zinc solution to the number of electrons gained by the zinc. They are equal. The number of electrons lost is always equal to the number of electrons gained. That is on purpose. It's the law of conservation. Magnesium is +2. Zinc is always +2, even though it's kind of a transition metal, it's always +2. So magnesium's always gonna look to gain 2. Zinc is always gonna look to gain 2. If they're gonna have a reaction, one of them obviously is gonna have to gain while the other loses, but it's always gonna be 2 and 2. Because it has to be equal by the law of conservation. Okay, question 80 says write a balanced half reaction for the reduction of copper ions. Copper ions, in this case, are starting out as +2, according to this table. Copper can sometimes be +1, so that was an important piece right there. I'm going to write this directly in my answer book. Oops. So we have copper ions, which are going to be +2. They are being reduced. We're asked about reduction. So if we are reducing, we are losing electrons, which means they're coming out. Right? No, we're gaining. Reduction is gaining. We're gaining 2 electrons. And then we are going to become a copper atom. You can put a little 0 there if you like. Okay, so one year I was teaching redox, the students decided that instead of it being Leo says GER, like lose electrons, oxidation, gain electrons, reduction, they wanted it to be Leo says GIRL with an L on the end. So it's still lose electrons, oxidation, but it would be gain electrons, reduction, left. And that means that the electrons would go on the left side of that reaction, of the reduction reaction. State why the student was instructed to clean the surface of the metal strips with sandpaper before placing each strip into an aqueous solution of the metal ion. They didn't say. I said it was to reduce oxidation. I'm curious what their correct answer is. Aside to make sure they're clean. Fresh metal surface. If a reaction will occur, it's more likely with a pure metal. Remove tarnish. Increase surface area. How would that... Oh, of pure metal. Including but not limited to. Okay. I don't like that they didn't talk about oxides in that little blurb. That's not something that I would argue a standard chemistry student would know. I don't love that. But let's see. To ensure metal is clean with no junk on it. Let's see. Residue that would interfere with the reaction. I think that's an answer that like a standard high school chemistry student would come up with. That's not oxidation. Because you guys are like in your first year of chemistry. You don't necessarily know that half of these things oxidize. Just from sitting in the air. I think that one's like not a cool question. Okay, last set. Two sets. Tetrachloromethane, CCl4, was used as a dry cleaning solvent until it was banned for its use in the US in 1970 due to its toxicity. The solvent was replaced in many dry cleaning processes by tetrachloroethane. Another currently available alternative dry cleaning solvent is 1-bromopropane. The table below shows the boiling points of those solvents. Explain in terms of intermolecular forces why tetrachloroethane has a higher boiling point than tetrachloromethane. It's a bigger molecule, so it has a larger dispersion force. That's really what it comes down to. They're going to talk about, like, it has larger electron clouds. It has stronger intermolecular forces. Larger dispersion force is that same thing that I just said in terms of intermolecular forces. It's really just because it's bigger, it has more electrons. And when the tetrachloromethane is here, ethane is here, it's bigger. When it like crashes into the wall or it crashes into another molecule, it like wiggles way more because it's bigger. The structural formula for 1-bromopropane. Okay, drawing organic molecules. To begin, we work backwards. We have a propane, and propane is 3 carbons, all single bonded. And then I have a 1-bromo, so I'm going to put a bromine on the first carbon. That could be the first carbon on the left or the first carbon on the right. Just make sure that it's on the end. And then we're going to fill in with hydrogens and make sure that every carbon has only 4 bonds. Most common mistake is to give extra bonds. Just like that. Last up, finally. When a neutron is absorbed by uranium-235 nucleus, the nucleus can split. One possible nuclear reaction is represented by the balanced equation below. That's an ugly equation, but okay. In this reaction, the products have a mass that is less than the mass of the reactants, but only by 0.18 atomic mass units. Okay. Compare the energy released per gram of reactant during this reaction to the energy released per gram of reactant in a chemical reaction. Okay. In nuclear reactions, we release, and we talked about this earlier as well. This test is like very repetitive. In a nuclear reaction, you have a small amount of energy and it becomes a huge, you have a small amount of matter and it becomes a huge amount of energy. And in a standard everyday chemical reaction, it's very proportional. So the nuclear reaction is going to yield or provide or release way more energy. Okay, and then finally, determine the time required for an 8 milligram sample of strontium-90 to decay only 2 milligrams of the sample, until only 2 milligrams of the sample remains unchanged. Okay, back to the reference tables where strontium-90 was an option of a choice. Strontium-90. I just wrote on top of it right there. The half-life of strontium-90 is 29.1 years. 29.1. Okay. Half-life. These are some of my favorite things to teach. Okay. We are working here with mass and time. We are starting with 8 milligrams. And this is years. We have 8 milligrams right now when 0 years have passed. But, what was it, 29.1? Yes, 29.1. After 29.1 years have passed, I now will have 4 grams of the strontium-90 left over. And after another 29.1 years, let's see. The total time passed will be 58.2 years, and I will cut in half. Divide by 2, and divide by 2. So I take my 4 milligrams, cut them in half, and now I have 2 milligrams, and then that should be it. So the final answer should be 58.2 years. Oop. And that is the number of years that it would take for me to get down to 2 milligrams. Let's just check on that. $58.2. Okay. That is everything. That was the August 2022 exam. Not my favorite one, honestly. Not that Regents exams are all that fun, but that's beside the point. If you are last minute studying, make sure to get some good sleep, good rest. If you have the time, what I would recommend is to watch the live stream that I did yesterday on the reference tables. That is a very good last minute thing because the reference tables are really going to guide you through a lot of questions. Also, I would review your vocabulary terms. Even just like skimming this test, find terms that you're like not sure of and just look them up in the glossary. That would be my 2 recommendations for the night before the test. Make sure to get to bed at a reasonable hour, get some good rest, go into the exam feeling full. Don't pump yourself up with coffee and have the jitters. Subscribe because I will be doing a stream tomorrow afternoon and then another one Thursday last minute to prepare you for Friday's test. And if you are watching the replay, of course, leave any questions you have. I'm happy to help you. If you need help finding a specific video to get to as well, you can request that in the comments here, and I will do my best to answer those in a timely manner. All right. I will hopefully see you tomorrow. Have a great day and enjoy the test. Bye.